In this video, we are going to explore how some variables, such as water level and exit area, influence the velocity of water exiting from a hole in a container. Before we begin our experiment, we need to take a look at Torricelli's law to know what assumptions we have to make. Consider a tank full of water, with a cross-sectional area A1 and a hole of an area A2 near the bottom of the tank. The liquid starts escaping through the hole with velocity v2. At the same time, the open surface of the water in the tank would drop with velocity v1. In order for the mass to be conserved, there would have to be a specific ratio between area and velocity at the opening and at the hole. Take Bernoulli's equation and assume that the pressure outside of the cylinder is just atmospheric. We set H2 equals 0, so we eliminate H2 from the expression. Plugging in V1 as an expression of V2, we derive an expression of V2 involving all the other variables. Since A2 is significantly smaller than A1, we come to the conclusion that V2 equals square root 2gh1. Note that by making this assumption, V1 also becomes 0, meaning that H1 will stay constant. The aim of our experiment is to verify that Torricelli's formula for calculating exit velocity can be applied by comparing the exit velocity calculated by the rate of mass change over water density times exit area to the exit velocity calculated using that formula. So we would need to make sure that the assumptions are met by selecting a container with a very large cross-section area and punching a very small hole in it. To begin with, we punch holes of diameters 1 mm, 1.8 mm, and 2.6 mm near the bottom of a square container with side length 18 cm. Then we tape them shut, add water to the container, and put it on a kitchen scale. For each hole that we're testing, the same initial water level is prepared, and we rip off the corresponding tape and record the changes in mass and water surface height over time. For the medium-sized hole, we analyze its mass change rate at two surface level heights with a difference of 0.1 cm. We calculated from our measured data that the exit velocity at the lower y is indeed slightly smaller than the exit velocity at the higher y. Additionally, the experimental exiting velocity matched the predicted velocity, thus proving that Torricelli's law is applicable in such a situation. For the large hole, we see that the experimental exiting velocity is smaller than what we got for the medium hole, but the expected velocity remained the same since we started at the exact same initial water level. Therefore, in this case, we got a larger error, which is reasonable because Torricelli's law applies better to cases with smaller holes and wider containers. However, for the small hole, we notice that water is not flowing out in a jet like it's supposed to be, and we got data that cannot be analyzed to support Torricelli's. We can only assume that this is due to the irregular extrusions around the rim of the hole resulting from bad cutting tools, which applied resisting forces to the exiting water. In another experiment where the same size hole was smoothly punched, this setback did not occur. In order to demonstrate a case where the assumption that container area far exceeds the hole area cannot hold, we conducted the same experiment using a smaller container. Notice how the water level of this container lowers significantly and betrays the prediction that H1 should be constant.